Hello and welcome back. The last UART video was ages ago, and that was because I finished the original plan for the UART PCB, made it, and it worked. But there's a couple of flaws on there. First and foremost is I wrote the wrong baud rate on the silk screen, and that's kind of annoying because it's a mistake, but it's purely cosmetic. And so I have been looking for a reason to refresh that PCB, and now I've got a couple of reasons for that. Firstly, on the PCB, I've got a crystal, and as I built more circuits inside the whole I/O subsystem, I realized I needed a clock circuit for those, and I've been using the same crystal frequency with a plan to output that crystal and share it among some additional circuits, notably the Snes Controller and the sound system. So it'd be really good to do a new version of the PCB with both the clock circuit output and the updated silk screen. But I've got another reason that I would like to experiment with it, and that's I want to add some hardware flow control. This whole system together is very much a demonstration system, and one of the key facets of that is the ability to modify the clock rate between the maximum rate I can run and a far slower interactive rate where you can see parts of the system interacting. But the problem with that is the UART, it's just too fast for that mode of the CPU. The buffer very rapidly fills up and it becomes a bad way to transfer data to the system. So that's one aspect that can't be very effectively demoed using the interactive clock frequency. Hardware flow control would let us continue to do that because it would allow the system to throttle to whatever the send rate was. I could switch it from 4 MHz to an interactive clock frequency where you can see the interactions of the internal parts. And so the addition of hardware flow control would allow me to still have that interactive experience and demonstration ability for the system, but without needing to worry about the UART overfilling its buffer. And this extra step is a little bit easier because JLC PCB have offered to sponsor this video. All the PCBs in this build have been made by them, but previously not as part of a sponsorship, but I'm very happy with their service, and I'll be talking about that a little bit more. Let's have a look. When people talk about flow control, there are two main types. You have software flow control, which is usually referred to as X on, X off. And this works by sending control codes over the main UART data lines. One that tells the sender to pause transmission and one that tells it it's okay to resume transmitting data. Now in this case, the receiver needs to be able to keep up with the data when it's focused on it, either directly or by monitoring a receive buffer, and it needs to be able to intelligently tell the sender when to stop. So this wouldn't really solve the problem of not having the CPU performance to keep up with the incoming serial data, but a common use case for this would be a data transfer program asking the sender to stop because it had to switch attention away to write data to disk or perform an other task. And the other type of flow control is hardware. Now, I most commonly see the variant that is referred to as RTS CTS. There are other types, but most importantly, on modern USB UART connections of the type I'm using to connect the CPU to my PC to transfer data to and fro, RTS CTS is the one that's supported by all of those that I've seen. So that's the one that I want to focus on here. So far, we've dealt with 3 lines: ground, TX, and RX. Ground lines are in common. The transmit of one goes to receive of the other, and vice versa. And for hardware flow control, we need some additional control signals. In this case, both local and remote device gain CTS and RTS lines, and they cross-connect in a similar way. So the first of these lines is RTS, which stands for request to send. Now that's the name of the physical line, but the signal that we're sending is actually better called ready to receive. Sometimes looking through the standards documents for any protocol that's been around for a few decades feels more like an archaeological dig. But today, all we need to worry about is that this signal indicates that the device sending it is ready to receive data, and therefore the device at the other end of the line is clear to send. I think now would be a good time to jump back to the physical build and actually experiment with some of these lines and get a better feel for what they do. Here's the UART control circuit with my shameful misprint of the baud rate on it. I've got the sending buffer and the receive buffer. Now the cable I've got that connects this, I had to replace at one point, and the new cable came with a few extra lines, and that included the CTS and RTS lines for hardware flow control. So I initially just made this adapter that allowed me to plug it into the RX and TX lines, but now I've added this wire that gives me access to the RTS and CTS lines as well. Let's power it up and see if we can look at the problem. So if we look at the receive FIFO buffer, when we send a character, you see the lights flicker that show the characters very briefly as they are sent from the host computer and received by the UART. Now what I can do is switch the CPU into single step mode. Now it's not going to respond, so any characters sent are going to fill up that FIFO buffer. So single character, and we've got one character in the buffer. Now, I've sent more than 8 characters now, and this is actually overflowed because it is only an 8-byte FIFO. And if I let it run, we'll see that flush out. Typing garbage like this into the monitor program isn't going to do us any favors, so I have written a small program that will help us out with that. So what this does is it just sits in a little loop, reading character in from the UART and then writing it back out, with some special handling for new lines and an escape character to exit back to the monitor. It's actually quite difficult to outpace the UART just by typing on the keyboard. So I'm going to solve this by pasting some text into the window. Now this is with the CPU running at full speed. So here I've got the test string has come out absolutely fine. But instead I'm going to switch the CPU down to trace mode, which drops the clock rate right down. And I'm going to paste it in and we'll see what happens. That's messed up completely. And what we can see is the last few characters are correct, but the beginning is both wrong and misses a large number of characters. And that's because we've just got this 8 bytes in the FIFO buffer. And the concept of the flow control is simply that we can send a signal to the remote device that says, I'm not ready, don't send data. So that will be the RTS line coming out of our system, which we don't have at the moment, going to the CTS clear to send line on the host. We need to look back here at the configuration screen for our serial terminal program. Now I've got the port set, the baud rate and the other configuration bits, but now we need to drop down here and select the flow control. Put that back to full speed. And now we have a problem. Pressing keys on the keyboard doesn't produce a character because we've got hardware flow control and we haven't said it's okay to send data. Right, I'd like to run some experiments with my bus tester. Clear to send, I'm going to put that into this switch here. Of course, as soon as I plugged it into the switch output, it's pulled the line low, so the signal is being sent, but it's clear to send. So this is able to get data. If I push the button, characters are not sent. But if I release it, it will flush that out. So somewhere between the hardware and the terminal emulator, the characters I type in are being held back and waiting for the signal that it's clear to send. Let's get the test program back in. Now it is going to be difficult to outpace what the UART can do just using the keyboard, but I think I can do it just by running my hand down the keyboard. So switch back to trace mode and I will try and do exactly the same thing again. And now we're seeing the system pulling those bytes in one at a time. And once again, the last few characters are correct, but the earlier characters are overwritten by later characters when we overfilled the 8 bytes of the buffer capacity. So still running at low speed, let's see if we can make this work by using the clear to send signal. I've pushed the button down when I got halfway along. Now I release it and bingo, the rest of the bytes come in. What we need is to repeat this process but have that signal generated automatically. I'm going to come in here and try and grab that top bit. So we've got 4 bits of output and an 8-byte buffer. So the binary representation of 8 is 1 followed by 3 zeros. So when the buffer's full, this top line goes high. So at full speed, pasting the text string in continues to work. At slow speed, what happens? Well, that's not looking good. So once again, the last few characters are actually correct, but earlier characters have been overwritten. And the reason why this has happened is because whilst the clear to send line has been sent high, meaning it's not okay to send, the moment this FIFO is full, the sending device is probably already sending a character. So that one's getting messed up, and possibly more because we've got no idea how much latency there. So what we need is to monitor the amount of data in the buffer and bring that line high when we're approaching full but not entirely full. So we're going to need to build a circuit. I need access to the count of bytes inside that line. So I'm going to see if I can solder a header onto here. Now you can under here see the little fly cable I've used to connect the clock signal to this point temporarily. Let's see if I can attach this pin header in, give us easy access to those lines. I won't win any awards for neatness, but I think it'll work. Alright, let's get the board back in. Need to connect that to clock line. It'll be really nice when the new PCB doesn't need me to do that manually. Connect the ground TX and RX lines. It should be ground and then the 4 bits of the receive FIFO count. Let's pull that low. First up, I want to confirm I'm actually getting the right data out of there. It might be easier to use this power line at the top. Daisy chain some power to my little tester here. And at this point, I'm just going to be using this for some easy LEDs. I'm going to leave that stopped. Now we're sending some characters. So yeah, 1, 2, 3, 8. I've proven I can solder a header on. Get that test code back in. We have a 4-bit binary value for a number of bytes in the receive FIFO buffer, and we want to set a threshold in order to trigger the clear to send line. Now I'd like to do this, if at all possible, with spare gates that currently exist on the UART PCB as it is. There's always a couple of spare whenever I build a circuit, and it would be nice to do this without adding any extra chips. So let's have a quick look at what we've got and the operations we need to do on that binary count. Now ideally we would do this with spare gates we've already got. So I've got 74HCT32, that's 4 OR gates and 1 is currently unused. I've got a HCT00, that's NAND gates and 1's unused, and another spare NAND gate. So we have 1 OR gate and 2 NAND gates. The receive FIFO has 9 different permutations of value which are valid from 0 to 8, and that comes in on 4 input lines numbered 0 to 3. But when we're trying to decode the binary value, it might be easier to think of those as having the values 1, 2, 4 and 8. So I've spent some time working out what I think is the simplest logic diagram comprising 2 input gates to uniquely do the greater or equal to operation for each of the 8 non-zero values. Greater or equal to 1 would be 3 OR gates. And of course, this is the same as we have implemented in the transmit circuit to detect if there's anything at all in the buffer, which is the same way as saying greater or equal to 1 byte. The value of 2 is quite simple. The 1 input line was actually irrelevant here, and just a non-zero value anywhere else was valid, so we can do that with 2 OR gates. 3 was a bit more complex. 4 was very simple, and is the first one that we can directly do with these gates. But it would mean we were telling the sender that we can't receive any data when the buffer is only half full, and I suspect that would limit our transfer rate. 5 is a very similar circuit to 3. Now 6 is quite simple. There's 7, and 8 is of course the simplest of all, but we tried it and it didn't work. So if the 2 we can actually do trivially, 1 doesn't work and the average is not very desirable. But while we don't have the exact gate matches for this, we can create an AND gate using the 2 NAND gates. So this circuit is going to tell the sender to stop sending once we hit 6 bytes in the incoming FIFO buffer, and I think that should give enough time for the sender to stop before we go past 8 bytes. Let's see if we can hack that into the existing circuit. Okay, so this is a NAND gate. Give it power and ground. I'm going to take bits 2 and 3 to 2 of the gate's inputs. So this is going to produce the opposite of the AND effect we want. So now we've got 5 and then we move on to 6. I expect the LED to extinguish, which it did. No real surprise there. And we want the inverted form of that. So by tying the inputs together, we can use the additional spare NAND gate as an inverter. So now that's going to be low. 1, 2, 3, 4, 5, 6. Let's come on. 7. But 8, it goes off. And 8 is still a valid level for the FIFO buffer. So we actually want to handle that. We also had the spare OR gate. So all the results are AND together with the top bit. So that's 8. Step through the invalid values. So 1, 2, 3, 4, 5, 6, 7, 8. Excellent. And all we actually need to do is output that on the clear to send line. Now that always worked at full speed, but now we drop it down to trace mode where the CPU is running at a very slow speed and it's not able to keep up with the UART. Now we can see the buffer is pretty much switching between 6 and 7 bytes in it. And that message is received correctly. Outstanding. So we've dealt with telling the remote device that we're not ready to receive data. But what about the circuitry to allow it to signal to us that it's not ready to receive? So we have an incoming CTS signal, and it's worth talking about how we control sending. So we have 4 incoming bits from the transmit FIFO, and we OR those together to perform that greater or equal to 1 operation, and that produces a signal in the circuit we call TX data ready. There is some data that needs to be sent. The easiest way I could work out to respond correctly to the CTS signal was firstly to invert it, giving us an actual CTS signal rather than the inverted form. And then we combine those signals with an AND gate to create a new TX data ready, which only goes high if the remote device is ready to receive. It's a very simple circuit with just one AND gate and an inverter. We could actually implement this with a 7400 for NAND gates. So we would use 1 as an inverter and then 2 to create an AND gate in the same way we did in the CTS generating circuit. Now, it was an interesting experiment to work out this circuit, and it's very simple. But try as I might, I can't find any way of convincing my PC to ever generate the signal to say it's not ready to receive. So I don't see much point in adding a chip to the circuit in order to handle a signal that it's never going to actually see. But I didn't want to ignore the signal completely. So now would be a good time to move on and look at the PCB update to include the CTS signal generation. So I've corrected the silk screen to have the correct baud rate on it, and I've added the clock output pin. Let's see if we can add the flow control functionality. Now we keep ground at pin 1. Now I want to match the header I've currently got on the end of this cable. I don't know how standard it is, but it's just going to make my life a bit easier. So the next pin is VCC, and we don't want to connect that. RX, TX, and then the other one would be the incoming RTS connecting to our CTS line, and we haven't done that. Receive FIFO counts. Right, the least significant bit's not relevant to us. Then we wish to AND these two bits together. That AND gate is closest. Then we OR that with the top bit, and that gives us the RTS signal. The other change I wanted to make was taking the receive line and giving that a pull up, because it did occur to me that whenever we have anything not plugged into this header, that's a floating input to the circuit. That's interesting. I've lost a header here. It's interesting the way it's named these nets from the continuation of when previously ground connected here. Let's see if I can update these. I wonder what happened to that line. This PCB was from before I started to use 4-layer boards. So I'm going to transition this to a 4-layer board, which is going to make this all a lot easier. We'll actually have a ground plane and a power plane to take care of all of this. Just need to get a good connection to the plane after the capacitor. That's improved the connections a bit, but we know the rest of the PCB works, so I don't need to rework it all. Let's hope this one works. I do want a stencil. As always, I want to customize the size. Customizing the size does not affect the amount you pay at this stage, but it does seem to affect the shipping cost. I do want to experiment with some of the other materials at some point. Looks quite interesting, but for now I'm finishing this big build with fairly basic 4-layer PCBs. So we've got the stencil as always. And it is good to see that with the correct baud rate on it. So JLC also sent me a sticker. And they've sent me a few demonstration PCBs. These ones contain the gold plating, which does look really nice. I don't know how valuable that is if you're not going to be leaving some contacts exposed. I really like the round PCB look. I need to find an excuse to make one of those in the future. I believe these are 6 layers, which is another thing that I would like to experiment with in the future. LEDs must all be the correct way round. The resistors do not electrically need to be, but I will get brutally attacked in the comments if I don't make them all the same way round. Because this was one of the NAND gate chips, 7400, we used a previously redundant one of these for the ready to receive signal. That was where we had a spare OR gate. Not sure when I nudged that. Let's stick my JLC sticker on here somewhere. Okay, I think that reflowed quite well. There's a couple of joints over here I wasn't so sure about. Yeah, definitely not sure about that. That feels right now. There's a couple of joints around here which do look different than the others. I think there's a pretty good chance they're actually okay internally, but it's very easy to become sure. I've also got to put this header on that we're going to use to connect the UART cable. I've just one thing missing, the oscillator. Just pulled this one off the main build. I think it would be nicer if the oscillator sat flush. Be a bit neater. That's beautiful. Let's give it a test. Right, let's get the old one out. In with the new one. Oh, that's incredibly promising. That appears to be working. Let's get that test program in. And let's test the flow control. Drop it down to the slowest speed. Looks to be working fine. I am really pleased with that. I've had a few PCBs recently that haven't worked first time and I've needed to do some bodges, so very pleased we got that one going. Awesome. And of course the ability for the UART to work now, even with the whole system in the trace mode with a very low clock rate, means that opens up some opportunities for demonstrating the system, particularly with all the lights blinking away, showing the interaction of different bits. I'm really pleased we can do that now. Don't think there's much else to do here. What can I say? We've achieved everything we set out to do. We've fixed the baud rate issue on the silk screen, we've got the clock output, and we've got the hardware flow control, or at least the ready to receive section of it. That's going to give us an awful lot of interesting functionality for the system when we're running in the slow clock speed interactive mode. As always, I'd like to thank my patrons and all the people who support me in various ways, even just watching and commenting on the videos. Thanks of course to the video sponsor JLC PCB. That was particularly interesting this time because we got to explore some additional functionality on the PCB compared to the previous version of the UART. I hope you all found it interesting. I'll see you again soon. Goodbye.